Welcome back to The Explainer, fellow engineers. Today, we're tearing down one of the most critical, yet surprisingly overlooked, safety nets inside a modern EV drivetrain. Specifically, we're dissecting the torque over limit via battery constraint, also known as the E05 fault, within the multi-motor power control system functional safety architecture. Now, when we talk about energy management and coordinating dual motors, we are literally operating on the bleeding edge of ASIL D, which, as you know, is the absolute highest hazard level in automotive functional safety. The stakes here, well, they're massive. We aren't just talking about a check engine light popping up. We are talking about completely preventing catastrophic battery destruction and making absolutely sure a driver never loses torque control, even in the most extreme edge cases. So let's establish our boundaries right off the bat. DPL, the discharge power limit, and CPL, the charge power limit. The battery management system, or BMS, is constantly dynamically calculating these safe operating windows based on real-time cell temperatures, state of charge, state of health, and internal impedance. If a dual-motor system pulls or pushes power past these incredibly strict boundaries, say during a violent acceleration or some aggressive regenerative braking, the consequences are severe. For instance, if you blow past that CPL, you trigger a massive reverse overcharging event. That physically and irreversibly destroys the battery's active materials, triggers thermal runaway, and in the absolute worst-case scenario, results in a total loss of vehicle torque control. Okay, let's dive into this roadmap. We'll start with fault root cause analysis, move to the SW/HW co-diagnostics architecture, check out DFMEA key design defenses, look at PFMEA manufacturing controls, and wrap up with DVPR production validation testing. Starting with Section 1, Fault Root Cause Analysis. We're zooming in on the invisible villains here. So how do things actually go wrong? We're looking at 4 major physical dimensions. First up, can FD high DVDT noise. Modern silicon carbide MOSFETs are incredibly fast, kicking out brutal voltage transients up to 50 volts per nanosecond. You guys know that kind of crazy DVDT slope injects highly destructive, high-frequency common mode noise right into the comms network, causing dropped packets for our battery power limits. Next is deep inductance saturation, which we'll unpack in a second. Third is priority inversion, basically unexpected software lag that delays reading a new power limit, causing a really dangerous timing mismatch. And fourth, busbar impedance wear. Imagine an assembly bolt missing its specific phosphate coating. When tightened, you get uneven friction, which means low axial preload. Over time, that becomes a localized high resistance point, creating a fatal voltage sensing bias that literally tricks the inverter into calculating the wrong power output. Let's dig deeper into that second root cause, deep magnetic saturation. There is a terrifying gap here between our digital software calculations and harsh hardware reality. Under heavy loads, the motor's stator core hits deep magnetic saturation, and the actual inductance drops off a cliff, totally non-linearly. If the field-oriented control, or FOC software, doesn't have a 2D LUT, a two-dimensional lookup table, dynamically mapping and compensating for this, the software calculation looks perfectly safe on paper. The MCU thinks it's staying right inside the BMS limits, but in reality, that deep magnetic saturation forces the real-world phase angle to deviate wildly from the FOC math model. The result? A massive physical overcurrent that just smashes right through the battery's safety floor. Moving on to Section 2, the SW/HW co-diagnostics architecture. This is the powertrain's real-time hero. Now, what's really interesting about this slide is the asymmetric dual-core lockstep setup. Think of the main MCU as the doer. It's sprinting at top speed, crunching insane FOC math to drive the motor. But right next to it, we have the checker. The checker doesn't care about complex algorithms at all. It is strictly monitoring the raw input and output signals independently, using raw, undeniable physical flux laws to supervise the hardworking doer. If the checker sees that the very next PWM command from the doer is going to break the battery's limit, it steps in instantly and completely cuts off the control signal. And this all has to happen insanely fast. We're talking about a 60-millisecond race against destruction to meet the ASIL D fault-tolerant time interval. In less than 100 microseconds, literally a fraction of a blink, the checker blocks the PWM gate drive signals at the hardware level. Power is cut. But wait, we still have a massive back EMF from the rotor's inertia, right? So in exactly 1.5 milliseconds, the system forces a two-phase short circuit to buffer that explosive runaway energy. Finally, safely under the 60-millisecond wire, it drops into a full active short-circuit state, aggressively clamping the bus voltage safely below 720 volts. It is absolutely lightning-fast engineering. All right, Section 3, DFMA Key Design Defenses. Let's see how we bulletproof this architecture. And this brilliantly illustrates how we fix the root causes in the design phase. To kill that software delay and timing mismatch, engineers hardlock the main MCU and the comms chips to a single shared hardware clock. This mathematically eliminates asynchronous timing lag, clamping the phase error to under 0.5 degrees. And what about that terrifying magnetic saturation we talked about earlier? Well, they bake a 2D LUT paired with recursively squares, or RLS, thermal algorithms directly into the base control model. Now the system has a feel for the hardware, instantly dynamically compensating when inductance drops due to high heat and massive current. Remember those brutal 50 volt per nanosecond transients from the silicon carbide switches? To stop that noise from completely freezing the data network, the design spec mandates that all communication isolation chips must have a common mode transient immunity, or CMTI, of greater than 100 kilovolts per microsecond. That massive isolation metric acts as an impenetrable electronic wall, using optical or magnetic coupling to forcefully block those lethal high-frequency switching transients from ever reaching the low-voltage logic circuits. Jumping into Section 4, PFMEA, Manufacturing Process Controls. This is where we bring extreme vigilance to the assembly floor. Here, human error is completely removed from the equation. To prevent that busbar impedance wear, modern plants use 100% servo-controlled torque angle fastening systems. They calculate the exact yield point of every single bolt to guarantee perfectly exact axial preload on the high-voltage busbars, bringing residual error down to an incredible 3% or less. And to make absolutely sure no uncoded fastener slips through, fully automated optical character recognition, or OCR vision systems, relentlessly scan and verify the part number and surface texture of every single bolt during feeding. Then we get down to the microscopic structural level. Less than 5%. That is the absolute maximum allowed total solder voiding rate under the microcontrollers and voltage sampling circuits. To enforce this, every single board goes through 100% inline 3D X-ray, or AXI. If the system detects a void larger than 5% inside a critical solder joint, that board is instantly scrapped. Why? Because you absolutely cannot risk extreme vibration and thermal shocks causing fatigue cracks that sever your critical voltage readings. Let's move to end-of-line testing and see how this builds into the ultimate trial. This isn't just a power-on check. This is merciless automated fault injection. While the dual motors are spinning on the dyno, the system injects a spoofed CAN signal that dynamically halves the battery's charge power limit, simulating a sudden battery cell overheat. The test rig then watches the safety architecture like a hawk. It must verify the system throws the P0A7F diagnostic code in under 10 milliseconds and physically confirm the motor G rates torque at an exact graceful slope of 500 newton meters per second to get safely back and bounce. Finally, Section 5, DVPR Production Validation Testing, the ultimate trial. This is where we literally beat the finished hardware to the brink of destruction before mass production. We have 3 core punishments here. First, over 1,000 hours of ISO 16750-3 triaxis vibration and extreme thermal cycling, just to prove those bolts won't loosen even a fraction. Second, 200 milliamp bolt current injection to try and violently jam the comms network with electromagnetic interference. And third, the grand finale, the FPGA hardware-in-the-loop battery load dump. Engineers spin the virtual dual motors up to a screaming 12,000 RPM and instantly snap the high-voltage battery connection. So, the crucial point is, even with all that massive kinetic energy suddenly having nowhere to go, the inverter's safety system flawlessly clamps the runaway voltage right back under 720 volts. Absolute, unquestionable control. Which brings us to a pretty mind-blowing thought, doesn't it? If a modern drivetrain can predict a microscopic anomaly, cross-reference it against the laws of physics, block the signal at the hardware level, and neutralize enough kinetic energy to destroy the vehicle, all in under 60 milliseconds, what else is your car thinking about before you even press the pedal? These invisible, bulletproof layers of protection are woven into every single millisecond of your drive. It really is an absolute marvel of functional safety engineering. Thanks so much for joining me on this explainer, and I'll catch you guys in the next one.